When performing electrical calculations for multi-family dwellings, it is crucial to adhere to the National Electrical Code, specifically concerning laundry circuit requirements. Even if a problem statement indicates no laundry, you must still account for the mandated 1500 volt amps for each individual dwelling unit. This requirement is firmly rooted in the NEC and is not waived simply because a dedicated laundry facility is absent. Article 210.52F of the National Electrical Code addresses the specific requirements for laundry receptacles. This section mandates that in dwelling units, at least one receptacle outlet must be installed for the laundry. This requirement exists irrespective of whether there's a designated laundry room or area within the unit. The code recognizes that occupants may still utilize portable washing machines or dryers, or they might opt to install their own laundry equipment at a later point. Therefore, the presence or absence of a built-in laundry facility does not negate the need for a dedicated laundry receptacle outlet. Article 210.11c2 further reinforces this by specifying the branch circuit requirements for dwelling unit laundry areas. This section dictates that in addition to the general lighting and appliance circuits, a separate 20 amp branch circuit must be provided to supply the laundry receptacle outlet. This dedicated circuit ensures that the laundry equipment can operate without overloading other circuits within the dwelling unit. The 1500 volt amp requirement is directly linked to this dedicated laundry circuit. It represents the minimum demand capacity that must be allocated for the laundry equipment. This value is based on the typical power consumption of washing machines and dryers commonly found in residential settings. Even if a dwelling unit lacks a dedicated laundry room or area, the potential for laundry equipment to be used still exists. Occupants might use portable appliances or choose to install their own equipment in other areas of the unit. Therefore, the 1500 volt amp allocation ensures that the electrical system can safely accommodate this potential load. Failing to include the 1500 volt amp laundry circuit in your calculations can lead to several problems. Firstly, it can result in an underestimation of the total demand load for the multi-family dwelling. This underestimation can affect the sizing of the service entrance conductors, the main distribution panel, and other critical components of the electrical system. Secondly, it can lead to overloaded circuits and potential safety hazards. If occupants install laundry equipment without adequate electrical capacity, the existing circuits may become overloaded, resulting in tripped circuit breakers, overheated wiring, and even the risk of fire. Thirdly, it can result in code violations. Electrical inspectors will verify that the laundry circuit requirements are met during inspections. Failure to comply with these requirements can lead to rejection of the installation and costly rework. To accurately calculate the electrical load for a multi-family dwelling, it is essential to follow a systematic approach. Firstly, determine the number of dwelling units in the building. This is the foundation for calculating the total laundry circuit load. Secondly, allocate 1500 volt amps for each dwelling unit, regardless of whether a laundry facility is present or absent. This ensures that each unit has sufficient capacity for laundry equipment. Thirdly, sum the individual laundry circuit loads to obtain the total laundry circuit load for the building. This value will be used in subsequent calculations. Fourthly, apply any applicable demand factors to the total laundry circuit load. Demand factors are multipliers that reduce the calculated load based on the likelihood that all units will be operating their laundry equipment simultaneously. The NEC provides tables with recommended demand factors for various types of dwelling units. Fifthly, add the adjusted laundry circuit load to the other loads in the building, such as lighting, general appliances, and heating/cooling equipment. This will give you the total calculated load for the multi-family dwelling. Sixthly, use the total calculated load to size the service entrance conductors, the main distribution panel, and other critical components of the electrical system. Ensure that these components are adequately sized to handle the expected load. Consider a hypothetical scenario. Suppose you are calculating the electrical load for a 20-unit apartment building. The problem statement explicitly states that no laundry facilities are provided in the individual units. Despite this statement, you must still allocate 1500 volt amps for each of the 20 units. This results in a total laundry circuit load of 30,000 volt amps or 30 kilovolt amps. Next, you would consult the NEC tables to determine the appropriate demand factor for multi-family dwellings. Let's assume the demand factor is 25%. Applying this demand factor to the 30 kilovolt amps laundry load yields an adjusted laundry load of 7.5 kilovolt amps. This adjusted load would then be added to the other loads in the building to determine the total calculated load. It's important to remember that the NEC is a minimum standard. In some cases, it may be prudent to exceed the minimum requirements to provide additional capacity and flexibility. For example, if you anticipate that many occupants will install high-end laundry equipment with high power consumption, you may want to allocate more than 1500 volt amps per unit. In addition to the 1500 volt amp requirement, the NEC also specifies the type and location of the laundry receptacle outlet. The receptacle outlet must be a 125 volt, 15 or 20 amp grounding type receptacle. It must be located within 6 feet of the intended location of the laundry equipment. The receptacle outlet must also be readily accessible and not obstructed by furniture or other objects. Furthermore, the NEC requires that the laundry circuit be protected by a ground fault circuit interrupter, or GFCI. This provides additional protection against electric shock in damp or wet locations. The GFCI will trip the circuit breaker if it detects a ground fault, preventing potentially fatal injuries. In summary, when performing electrical calculations for multi-family dwellings, always include the 1500 volt amp laundry circuit for each dwelling unit, regardless of whether a laundry facility is present or absent. This requirement is mandated by the NEC and ensures that the electrical system can safely accommodate the potential load of laundry equipment. Failing to comply with this requirement can lead to underestimated loads, overloaded circuits, safety hazards, and code violations. Always consult the latest edition of the NEC and any applicable local amendments to ensure compliance with all electrical codes and regulations. Electrical calculations also involve considering various factors that can influence the overall load demand. These include the size of the dwelling units, the types of appliances used, the occupancy patterns, and the climate. Larger dwelling units tend to have higher electrical loads due to the increased number of appliances and lighting fixtures. The types of appliances used can also significantly impact the load demand. For example, electric ranges, ovens, and water heaters consume significantly more power than smaller appliances like toasters and coffee makers. Occupancy patterns also play a role in determining the electrical load. Buildings with higher occupancy rates tend to have higher overall load demands due to the increased usage of appliances and lighting. Climate can also influence the electrical load, particularly in regions with extreme temperatures. In hot climates, air conditioning systems can contribute significantly to the overall load demand. In cold climates, electric heating systems can have a similar impact. To accurately account for these factors, electrical engineers often use load calculation software. This software allows them to input detailed information about the building, the dwelling units, the appliances, and the occupancy patterns. The software then uses this information to calculate the expected electrical load for the building. Load calculation software can also help engineers to optimize the design of the electrical system. By analyzing the load calculations, engineers can identify areas where they can reduce the load demand and improve the efficiency of the system. This can lead to significant cost savings over the lifetime of the building. In addition to load calculations, electrical engineers must also consider voltage drop when designing electrical systems. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause appliances to operate inefficiently or even fail. The NEC specifies the maximum allowable voltage drop for branch circuits and feeders. Electrical engineers must ensure that the voltage drop in their designs does not exceed these limits. To minimize voltage drop, engineers can use larger conductors or shorten the length of the circuits. They can also use voltage drop calculation software to analyze the voltage drop in their designs. Another important consideration in electrical system design is grounding. Grounding is the process of connecting the electrical system to the earth. Grounding provides a path for fault current to flow back to the source, which helps to protect people and equipment from electric shock. The NEC specifies the requirements for grounding electrical systems. Electrical engineers must ensure that their designs comply with these requirements. Grounding systems typically consist of grounding electrodes, grounding conductors, and equipment grounding conductors. Grounding electrodes are metal rods or plates that are buried in the earth. Grounding conductors connect the electrical system to the grounding electrodes. Equipment grounding conductors connect the metal enclosures of electrical equipment to the grounding system. In addition to grounding, overcurrent protection is another critical aspect of electrical system design. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect the electrical system from overloads and short circuits. The NEC specifies the requirements for overcurrent protection. Electrical engineers must ensure that their designs comply with these requirements. Overcurrent protection devices are typically installed in panel boards and switchboards. They are sized to protect the conductors and equipment that they serve. When an overcurrent occurs, the overcurrent protection device will trip, interrupting the flow of current and preventing damage to the electrical system. Electrical system design is a complex process that requires a thorough understanding of the NEC and other applicable codes and standards. Electrical engineers must consider a wide range of factors to ensure that the electrical system is safe, reliable, and efficient. By following the guidelines outlined in the NEC and using appropriate design tools, engineers can create electrical systems that meet the needs of their clients and protect the public from electrical hazards. In the context of multi-family dwellings, another crucial aspect is the coordination of the electrical system with other building systems. This includes coordination with the mechanical, plumbing, and fire protection systems. For example, the electrical system must be coordinated with the mechanical system to ensure that the heating, ventilation, and air conditioning equipment has an adequate power supply. The electrical system must also be coordinated with the plumbing system to ensure that the water heaters and pumps have an adequate power supply. Furthermore, the electrical system must be coordinated with the fire protection system to ensure that the fire alarm system and sprinkler system have a reliable power supply. Coordination between these systems is essential to ensure the overall safety and functionality of the building. Building information modeling, also known as BIM, is a valuable tool for coordinating electrical systems with other building systems. BIM is a digital representation of the physical and functional characteristics of a building. It allows engineers to create a three-dimensional model of the building and to visualize how the different systems interact with each other. BIM can help engineers identify potential conflicts between systems and to resolve them before construction begins. This can save time and money during the construction process. In addition to BIM, other software tools are available to help engineers with electrical system design. These tools can automate many of the tedious and time-consuming tasks involved in the design process. For example, there are software tools that can automatically generate panel schedules, calculate voltage drop, and size conductors. These tools can help engineers to improve their efficiency and accuracy. As technology continues to evolve, electrical system design is becoming increasingly sophisticated. Engineers must stay up to date with the latest codes, standards, and technologies to ensure that their designs are safe, reliable, and efficient. Continuing education is essential for electrical engineers to maintain their competence and to provide the best possible service to their clients. This education ensures that you stay aware of changes to rules, which often occurs every 3 years. Moreover, you must check with the local jurisdiction for any changes to the NEC in your jurisdiction. As the NEC is a recommendation and not a legal requirement, some jurisdictions may change, modify, or add to existing rules in the NEC. For example, some jurisdictions may require arc fault circuit interrupter protection for circuits not required by the NEC. Be sure to check with your local jurisdiction to see what changes have been made. These changes will also affect load calculations.